friends, let's stop doing stuff for a second, please. Here's a little, let's play a different game. Closing our eyes and just lightly putting our forefinger and thumb together. Not in the cheesy way you would see in someone in an ad holding their hands up in a mudra. Just a light pressure. And bring your awareness to that sensation. Notice how it changes constantly. Back gently over and over again to noticing that sensation. Whatever's going to happen. Not quite sure what's going to happen. Except that I'm going to ask you what you want to happen. Does anyone have anything they want to chat about? Like problems or homework or anything? We have a homework assignment out, right? When does that due? Friday? Or next week? What? Somebody help me out.
Today?
Oh, today. Technically today. Yeah. But, I'll take stuff up till Friday, as always. Is there something, Morgan, did you want to talk about anything? Or you want me to maybe we could look at what's going on there?
I was just, the last question, just kind of where to start it.
Oh, cool. Yeah, I'm sure you're not the only one with that question. You're just one of the few who have started that question. So that's nice. Cool. What is the last question? My goodness. Let's see. I'm sorry, which one?
Oh, dilations. Yeah.
Dilation. Yeah, cool. So the general formula, we'll go over this in a second, but the general formula for a dilation is Kz. So I'm actually not quite sure. I guess they use dilation for both expansion and contraction. Is that true? Or are they just talking about, yeah. So that's weird. That seems weird because I think of dilate as to widen. But I would think of this as a scaling. I like that a little bit better because it's arbitrary. If K is bigger than 1, it's expansion. If K is less than 1, it is contraction. So here, this will just take everything, this one, the way we're given it, takes everything at the origin and moves it away by a factor of K. So it'll take the point 2 plus I and multiply everything by K. So let's say, for example, S of Z equaled 3Z. It's going to turn that into 6 plus 3Z. But really what it's doing is it's just moving it along this line and stretching it out in that direction. So it's going to scale that out to 6 plus 3I. And it's doing that everywhere. So if I had a point over here, it would end up moving out this way by a factor of 3 units, or factor of 3 away from the origin. So for this one, they are saying find an equation for dilation around any arbitrary point. So what we're going to do here is use the schemes that we kind of practiced last time. And the first thing I'm going to do is, I'll give you the steps for it. So move the Z naught to the origin. Step 1 is to just take this thing and move it to the origin. Step 2 is then dilate. So is this making sense, Morgan? So I want to translate to the origin, then dilate, scale, so multiply by k. So this is going to be something in here, and then I'm going to have k times that something, and then I'm going to move myself back to here. So think of this in general. Whenever we want to scale or rotate, we always have to do it at the origin. So you have to move yourself there, do what you're going to do, then move yourself back to where you were. So then move back to Z naught. And when I say move here, Morgan, I'm saying just translate. So just a plus or a minus on those things. Does that help a little bit?
Yeah.
Yeah, cool. Anything else you'd like to chat about? That's the DIA tram sound. I'm pretty damn positive. Okay, we'll have a quiz on Monday. No problem. There will not be a problem. Although some people have makeup problems to give me by Friday, but there will be no problem on here. This is just know these things. So first off, in your own words, explain inversion in the unit circle. So I'm literally talking about the most primal one. Here's 1, I, minus 1, minus I. What does that mean? You can use equations, which probably are the easiest way to do it. But what I want you to do in all 3 of these things is treat it like you're talking to someone you're educating. Don't assume I know what's going on. Pretend you're a tutor for this class. I know that sounds terrifying. It actually would be terrifying for me to be a tutor for this class. But all the details. So this one here, formula for inversion in an arbitrary circle. That's just a formula, but what do the little pieces stand for? Right, so know that statement well, and then know this one here. We're going to start lifting off and talking about basically circles and lines are going to become the same thing for us at some point. And so we're going to call them clines, which is kind of cool and weird. What is the equation of a cline? And just know those details. So this is a matter, how would you study this? How would you do this? Can someone tell us like how you're going to prep for this? Read it once, hope for the best. What I would do is read it, write it, put that away and try to write it again, right? That's how I would memorize it. I'm not sure, I mean, I hope that's, you figured out by the time you're in a 400 level math class how to learn shit. But sometimes people aren't quite certain. They think they're supposed to just be able to get that instantly. Does this make sense to everybody? We cool? Because the details are what I'm going to grade you on. I was really loose on that last one with the, I asked somebody, there was some box I asked folks to give me. I took almost anything. I'm going to be a little more uptight about these. Is this good? Yeah? No problem. Just know those definitions and those formulas. That's it. Because that will be good and helpful for you. So we need to finish up section 3.1, which is kind of what I want to do today. And I want to warm up first. Here's a little warm up. I'm going to give you a transformation. And I'd like you to write a sentence about what that does geometrically. Or draw some pictures or something. What is that doing geometrically? Takes a point Z and does what to it? So let's just spend a few minutes thinking about that. Yes, I'm recording.
not sure I'm recording. Dang it, I was. Oops. Oh, okay. Well, I guess I'll have to edit some video. Ooh, is this for me? That looks so good. I'll take that. Yes, if you have stuff for me, thank you. I'll have your last assignments back on Friday. You pick them up at my office. If you have this for me, I'll take it today. If not, I'll take it Friday. Thank you.
So I don't know if like the way it was done was the same, but it helped me understand it.
Cool. Awesome. Yeah.
If the steps aren't exactly the same, like for example, this one and this one, the steps are.
I'll give you feedback.
I did
I'll
this
let
one.
you know.
Yeah, I did this one like we did in class and this one.
That's awesome. That's cool.
So just cause.
I appreciate that you dug in and figured out what needed to happen to make it happen. Good,
Yeah, I just
good
wanted to
work.
let you know it's gonna look good.
Gonna look a little
Yeah.
unfamiliar. Cool, thank you. Many thanks. And I'll get. Is this for me? Okay. Kitra, thank you for replying. Apparently they already had people by the time I replied, but thank you. Is this making sense? This is all I'm looking for, just that we can look at that and understand what is happening geometrically. There's one thing I've been wanting to point out. I think about it every time class ends. I wish I had talked about this. This isn't the only way to think about this. This isn't the only way this could be written. And what I mean by that is, what if I did a little algebra and turned it into this? So now it looks a little different, but it's the same thing. And the one way we could interpret this is, there's multiple ways to accomplish the same linear transformation in the plane. So this one here says, and you can think of scaling and rotation. These could be in either order. There's no order here because multiplication's commutative. So this could be scale by 2, so this is first. 2, rotate, and these two are interchangeable, by 60 degrees clockwise. And then 3, just shift by whatever this point is. Now I'm not going to claim what that is because it's got positive and negative parts for it, but then just shift by -2 e to the negative pi over 3i. So same thing, this will get you to the same place, but it looks really different and also sounds different. So by taking the math and doing the math that we know, we can gain intuition and understanding about the way things roll. Is there any questions on that, friends? Is it good? Good warm up? Okay, cool. So I'm going to reference the book a lot because I kind of want to just get a couple of these pieces at least noticed as a group. So I'm looking at page 32. That was the first thing I wanted to look at. Yeah, and I guess we just kind of reviewed 32. 32 is just
basically what we talked about here. It's how to look at a transformation, the box on page 32. It's how to look at a transformation and understand what it's doing, or to create one, go the other direction. And so we've got that. They do have this little bullet point in there. Reflection across a line is this. Reflection across a line is e to the I theta z conjugate plus b. They don't give you much details here. What theta is and what b is are going to be, you're going to have to build those up. So you can take every reflection across a line, L. So if this is Z, and this is its reflected image, R sub L of Z, that's going to look roughly like this, but what theta is and what B is going to vary a lot. So this thing is just kind of a vague sense. But notice that piece. That conjugate is the flipping piece. So when you see conjugates in any transformation, notice they aren't in this kind. The general linear transformation looks like this. It does not involve flipping. You cannot get that flipped any way other than that. So just some good little notes to keep in mind. Please definitely read the book too, because there's stuff in here that we don't talk about. Let's see, Theorem 315 I wanted to hit. That the composition of two transformations is also a transformation. I just kind of prove that really quick. So if I've got a transformation that looks like this, and I've got another one that looks like this, what does this notation mean?
You're doing S first and then T.
That was just what I wanted to hear. Thank you, Christian. So this says do S first, then T. So remember, if you have an argument here, this is S first, then T. And you could actually crank out a formula for this. So let's just do that really quick. This just turns into another transformation. And there's a good point to understanding this, or a good reason to. So let's see, so this is going to be A, S of Z plus B, and then this is going to be that formula there, plus B. And so when I work it all through, I've got AC, Z plus, and then I've got a new constant out at the end. But notice this is just another one of those, of that form. So if I just take two of these transformations, it's another one. Nothing weird, nothing heavy. All right, what other box did I want to take a look at? Yeah, definition 318. So in definition 318, we talk about the image of a set. I'm going to ask for some help here. Let's see, I have a transformation that takes some subset of the plane into itself. So T is a transformation. What I mean by this might even look really weird. Here's the complex plane. All this is saying is that I've got some weird set A maybe, and this thing takes a point inside here and it lands back inside here, always. So this notation means if I eat from set A, I land back in set A. Just to talk about that notation there. If D is a subset of A, and that just means D is some subset of that set there, some sub-collection. Then T of D is the image. This is just terminology. The image of D under T. So that's the way we would say that. Let's do a practice run. Let's find an image of something. And we've done this a couple of times, but I've got one in mind. Let's say that T takes complex numbers and turns them back into complex numbers. And in fact, T of Z is going to be exactly, what was the dude that I had in mind? Oh, here. IZ minus 1. So what if my set D is this square right here? So I've got a square, it's got 1 plus I there, it's 1 there, it's I here. Here's my set D. What is T of D? So draw it is, I guess, what I'm looking for. Draw a picture. There's like a secret little thing in there that I really wanted to point out. You might want to think about what I is in polar form to help understand what multiplying by I does, because it's actually one of our more important multiplications. Writing it like that actually helps us see that. Oh, that's nice. That's shockingly nice. I think I'm getting that right. This is the rotate part. Oh, this turned out cool. This isn't the one I wanted, but I like it a lot. Does that look like it rotated 90 degrees? Yeah, because then this side, because we're pivoting here, this side ends up there, and then, yep. So let's see, so it's like that. Turned on its side. And then we shift it 1 unit to the right.
Wouldn't you shift it to the left?
Yes, thank you. Yeah, thanks, Lou. Yes, you absolutely would. Because that is subtraction. Thank you. So I would which is less cool, right? Shit. Whatever. Okay. I hate that now. Shift it to the left. -1, -2. There's I. So whatever. There you are, bro. Thanks, Lou. No, I'm not being sarcastic. I'm not like, thanks, Lou. Thank you, because I would have fucked it up.
You could have just changed the original problem.
I thought about that too. I did think about that, because it would have landed right back on itself, right? If I'd had +1, that would have been pretty. It would have landed right back on itself, just rearranged somehow. Cool, so that's how you find images. Any questions on that one at all? Let's do some chill work. Very good. All right, let's look at something a little heavier. Any transformation sends lines to lines and circles to circles. Now I want to spend a few minutes talking on this. So this is some theorem in the book. I don't quite know which one. but we have a theorem that says any linear transformation. Let's be clear about what we mean. An A is not 0, because otherwise it just crushes everything to B, so I definitely don't want a 0 Z in there. Any linear transformation sends lines to lines and circles to circles. Lines and circles are going to be our bread and butter in this class. They're literally going to be the thing we spend the most time on, which seems kind of weird, but it is what modern geometry is all about. So let's do a little proof. Let's at least think through how we would prove this. So the first thing I would ask you is, can you on your own, what is the equation of a line? So suppose L is a line given by, can you write out the general equation for a line, please? We'll practice along the way. Anybody got a line equation for me? You two look like you do.
I mean, I said mx plus b.
That is true.
That is a line
Can I have it in Z form?
in z form.
Yes, the complex form. So yes, Olivia.
Is it alpha times z plus alpha times conjugate z?
Yes, alpha conjugate times Z conjugate, yes. Plus D equals 0. One of the little deets about this that's important is D is a real number. So, ladies, you were absolutely correct. So you're probably thinking, why is he asking us this? Because the funky form. Thank you. So this is our L. And just keep in mind, this D is a real number. Alpha is not a real number. But it's it and its conjugate appear in here in this way. So let's assume, what we want to do is show that T of this line equals a line. So I'm just going to kind of abuse notation here just a little bit. What I'm going to show is that any point in T of L is actually on a line equation of its own. What do I mean by this? So we will show that all the points in T of L have this form. Have form star. It's going to be a different alpha and a different D, but we're going to show that if I take any Z that fits this form, run it through that T, that the output will also be a line. So let W be a point in the output. So this is W is an element of the image of L. So this is the image of the line under T. And I'm going to show W satisfies some equation like this. It's actually pretty straightforward and kind of nice proof. Watch how we unfold this. It's really quite lovely. So the only thing I really know is that Z does this, and T looks like this, and W is in T of L. So since W is, bless you, in T of L, W must equal T of Z for some Z. And that Z is in line L. So let me stop, read that, and make sure that that sentence makes sense, and if not, let me know, and I'd happily explain what I mean here. So I'm taking a point in the image of L, and so it must come from some input. So this is the output of some Z under T. And I know what T looks like. So W is equal to AZ plus B, just by the definition of T. And now I can solve for Z. You see, this is a cool little trick. So subtract B and divide by A. And since A is not 0, it's all good. And we're going to now, since this Z came from here, I'm just going to replace these Z's with that formula there. So plug this representation of Z into the equation. Let's just write it out again so it's just right here for us. And then we're going to simplify and show that everything turns back into that rhythm. We are looking to see that this rhythm is true of W as well. So I want to do that, and you can work along with me if you want. I kind of won't say every word. I'm just going to write it through here, especially for those who just want to do it on their own. Be careful with that conjugate. A and Z are complex numbers, so when you do this, you've got to spread that conjugacy everywhere. So I might slow down on this one. Just do a little bit at a time. Just sharing that conjugate love to everybody. That one, and that one, and that one. Everybody gets them. Bless you. And you'll start to see that this is becoming just a fancy looking line form. Wait, what have I got here? M7 alpha. Yeah. Lordy. And there's only one more step then. Make sure you're following me here. And if you're already here, my question for you is, why is this a real number? Because A and B aren't. A and B are complex numbers. So notice how we do have the form. We've got some constant times a variable plus the conjugate of that constant times the conjugate of that variable. And we just want to show that we have a real number here equals 0. But we have shown that W falls on a line. So T, if Z is on a line, its output is on a line. Not the same line, a new line. Got a weird ass equation. And I will be even a little bit more helpful. Oh, hey Morgan, hi.
Under the part that you did the little squiggly, is it supposed to be alpha B over A, or is it A B over A?
Thank you. I think yeah, that's a good call. You busted me on that one. Thank you. Good bust. Many thanks. Let me fix. Yeah, because otherwise I should have just canceled it, right? Good eye. Thank you. So yeah, alpha and B and A are complex numbers. D is real, we know that, because it was part of a line, so we know that's real. Why is this piece real?
Wouldn't it just be the conjugate of some
Yeah, exactly, because I've got a sum of a complex number and its conjugate. Think about how that works. If you have a complex number that looks like this, and you add it to its conjugate, what do you get? The imaginary parts cancel out, and you're just left with the real part. So because I've got a complex number plus its conjugate, I get a real number here. Because the imaginary, just like Vivian said, the imaginary parts cancel. Cool, now we know transformations take lines to lines, which we could also completely convince ourselves of knowing what this does. It rotates. Rotation just changes the line's orientation. It scales, that just blows the line away or brings it in. And it rotates. Rotating a line gets you a line. But now we've proven it without just kind of some sort of heuristic argument where we're imagining things happening. Now let's do, this one is supposed to be a homework problem. We're gonna do it together. Circles get mapped to circles. I'm gonna need your help here. Let's start with the circle. So we're gonna do T of Z is good old AZ plus B. Somebody help me. Here's a circle. Here, I'll draw one. It's got C naught. It's just, oh, well, that's, you know, give me a break. I gotta go to that dinner, so I'm probably not gonna, that's my excuse for everything today. Oh, my wife is so sick of hearing me bitch about that dinner. Baby. Boo-hoo. I just don't like being out at dark. I'm scared, I'm an old person, you know, I see teens on my lawn and they're coming to get me. Can somebody, what is the equation of this circle? There's at least a couple answers that seem good. Well, we had a quiz. We had some kind of a quiz, right? Yes, you could even look at that quiz. Correct.
Oh, wait, let me see.
Or,
Got it.
oh yes, Morgan, give me a.
The absolute value of Z minus Z naught equals R.
Beautiful. There's one. Hell yeah, thank you, Morgan, you saved the day. Now give me another one. I'll give you this one. We haven't talked much about this one. I've been waiting for it. So let's think about how you get a point on this circle. So first thing, how would you make that circle there? Well, the first thing I would do is take the unit circle, 1i minus 1 minus I, and that just, everything on there looks like this, right? Everything on that unit circle is of this form. In fact, theta is exactly that measurement right there. So if I let theta run, I spin around and I spin around the circle as theta grows. Cool, so a little unit circle at the origin looks like this. How could I make this circle a circle of radius r?
R at the front.
It's r the front, yeah, exactly. Is that what you said? I like it. Yeah, r the front. Slap an r on the front. Scale that shit by r. So then I take that and I multiply by r, and kaboom, I've got a bigger circle. Thank you, Christian. That row is really knocking them out of the park today. You row over there. You two are carrying some things for us. So we got still at 0. So now I've got unit. Now I've got a circle of radius r. How do I move it to z naught?
Unit Z naught.
Thank you. We add z naught. So then translate. So this is scale. And then translate to by a plus z naught. So this is beautiful. Those quizzes are really sticking, huh? Translate it as z naught, and here's what we get: r e to the I theta. And then as theta changes, you get your circle traced around. Theta is a real number. That's a way better one to work with if we're going to do algebra. Yeah? Yeah. So help me out here. Let's do this one together. We're going to take a point on here, and we're going to show that this thing, turns into a circle. So everything here, how about this? Suppose that z equals z naught plus r e to the I theta. So in other words, it is a point on this circle here. What is t of z? Can you take a moment and convince yourself that you still have a circle? And what is that circle? So just take a moment, because t of z is right here. We've got a nice old equation. What does it do? Where do we go? No one's proving it. We don't ever have to prove it again. Note some things to notice. Cool. Get some algebra that looks like that. What does our new circle look like? How would you describe it in words? Where's our new circle? What's its radius? AR. It's this number in front. So the output is a circle of radius AR. So the radius gets scaled by A.
Cool. And where's my new center? Right here. So it literally just picks up the old center and moves it as it moves every other point. Circles go to circles. Lines go to lines. And that will become a good piece of knowledge to have. Any questions on that, my friends? I've got a couple of, I got like one really major thing that I want to talk about, but I wanted to make sure we just at least touch base on some of these basic facts. Cool. So there's something else I wanted to point out. Where was that? It was on page 36 bottom. I think we did that, okay. Theorem 3.1, oh, Theorem 3.1.12. I'm not gonna prove this one, please read this proof. So I'm gonna leave this to you to read through, please do, because it has techniques in it. The author wrote this book with the hope that you would read the book and the proofs, because they have magic and gold inside the proofs. And sometimes you will learn a lot just by reading a proof. So, but this theorem, Theorem 3.1.12, says that linear transformations preserve angles, not ankles. Linear transformations, good Lord, preserve angles. Let's talk about what that means just quickly with a picture. So what does that mean? That means if I had, for example, in the plane, I have a point Z naught, and I've got a ray coming off of it there, and a ray there, and that angle is theta. Let's call that line 1 and that line 2. That when I do this thing to it, it's still theta. These are gonna get shifted. This is gonna get rotated. Things are gonna get scaled, but it's still the angle theta. So when we come out over here, and we've got T of Z naught right there, and maybe this is T of L1, and we know that lines go to lines, and here's T of L2. And I kind of almost didn't make it look like theta, but that's still theta in there. Has nothing weird is happening. You're stretching the lines, you're rotating, and you're translating. So it seems pretty reasonable that that would happen. What seems less reasonable are the last two things I want to talk about today. God, I don't know if I might have to look in my notes to check out these proofs, but I went through them a couple of times. So here are two fundamental results that come up over and over again from here on out. It's gonna turn out that all of our work, you keep it together, you can do this, I know. I see, fading fast, we're almost there. It's gonna turn out that almost everything we do in here is a reflection over something. Even translations turn into reflections or can be described by reflections. And this was the part of the class that just, I told you how I was all upset before the class started. I was freaking out. This was the thing that I didn't get, that I do get now. But it was kind of a leap and it scared the hell out of me. So the first one is, every translation can be thought of as a reflection over two lines, as consecutive reflection over two lines. Let's just talk about that first. And then once you understand this, the rotation one, that word is consecutive. If that's not clear. So let's say I have this translation
that just looks like this. I'm gonna put a little sub B here because our book does that. But this thing just moves everything by B. So, how can we see this as two reflections? What are the lines, right? Because this thing, for instance, takes 0 and it shifts it to the point B. And so we're going to use that as kind of our anchor, excuse me, in this process. I need to figure out what are the two lines I'm going to flip over. So here's how this rolls. Oh, that's good. That's good. That's good. Okay. The old man. This is super old man, right? I got my lounger. So the first line is a perpendicular to this line segment through the origin. So line 1 looks like this. We'll call that line 1. And I guess maybe I'll make him solid. I wish I had multiple colors with me, but I'd have to get up to get them. So you see my problem. And the second line is formed by taking the perpendicular bisector, so this is a right angle, perpendicular bisector of B, which is parallel to this line as well. So these are both 90-degree angles. This point right here is B over 2. So here's how it works. Once you know these lines, that's the hardest part. This would be the hard thing to come up with if you had never seen this before. The plan is this. We take Z over here, we flip it over line L, and then we line L1, then we flip it over line 2, and that gets us our translation. Now I'm going to prove that to you. So, all right, I'm going to get up now. So this will equal reflect, I'm just going to summarize what I want to prove here. Reflect Z over line L1, then that result over line 2. All right, so what we need to do to see this is to draw a line parallel to this segment here from 0B from Z. So I'm going to draw a line. So again, these are perpendicular, just like that. So this line segment is parallel to B over here. And I'm going to mark off where that line intersects these two. So that's going to be called Z1, and that's going to be called Z2, right there. There's actually some really cool thinking that'll go into this, because we're going to think about what it means to do a reflection as a translation. So to prove that a translation is a reflection, we're going to think of reflections as translations, which is kind of cool. All right, so let's first take the reflection over line 1 of Z. So this notation, reflection over line 1 of Z. What that means is that I just have to notice what this distance is right here and move that same distance onto the other side. Does that make sense? Yeah? So to take this distance and just move that distance over here. Well, what is this distance right here? It's Z1 minus Z. So I'm going to take Z1 and add on Z1 minus Z. And then that'll shift me right over here by the appropriate number of units in the appropriate distance. So this turns into 2Z1 plus minus Z. Cool. Now we're going to go over R2, or L2. So to flip R, little r over L2 of Z, let's just write out the general formula. Could you actually do that to make sure you get this? If you have a Z right here,
what is this formula going to be in terms of z and z2? Let's just write it out together to make sure you're getting it. So hungry. They better have vegan food at that dinner. Can someone give us the formula, please? Just gonna lift a finger for each second that goes by.
Is it Z2 plus, in parentheses, Z2 minus, and then the point from?
Quite beautiful, thank you. And I didn't have to fall back, which I was quite ready to do, but I didn't really want to. So you're gonna take Z2, this point, and add this distance to it, which is just Z2 minus Z. So that's 2Z2 minus Z. So now let's compose these suckers. We're gonna do R of L2 last. So we're gonna do this. We're gonna find that composition. First do this, then do this. So that's RL2 of RL1 of Z. And now I can go to this formula right here. And so this is going to equal, I'm just gonna replace this Z2, or excuse me, that Z with this thing here. So this is 2Z2 minus R of L1 of Z, right? In place of that Z, I have this formula right here. So that's just going there. And now I'm gonna pull that formula out. That's 2Z2 minus, in parentheses, that a top formula. And so then that simplifies to 2 quantities Z2 minus Z1 plus Z.
Why is that our original transformation?
Why is this Z plus B? What you think? Yeah.
Well, because you have. I'm trying to explain it, but it has something to do with the distances of the little lines on B are comparable to Z. And then it's B over 2, so it gets rid of the 2.
Perfect.
But I'm not.
Oh, that's so good. You see what's happening. Sarah, let me help you say what let me say what you said there, because I heard it. I heard the right thing. So this distance here is B over 2. These are parallel lines, so this distance is B over 2. So in other words, Z2 minus Z1 is B over 2. And there I have twice it. So it's 2 times B over 2 plus Z. Huzzah. It's just B plus C. Nice. So it seems, it's like, wow, that's actually not that deep or anything. It's kind of cool. I would have never thought of it, but it's, you know, we're doing it together, so it's nice and safe and feels good at this point. Let's do the rotations. Hold on, we'll probably end a little early today, so we can go take naps at math club or whatever. Okay, so any rotation is can be described, let's say by theta here, can be described by 2 reflections as well over
lines, but lines through the origin this time. And all I have to do is show you what the lines are, and then we can figure it out. And I wouldn't have known this unless I read the book. So what are the two lines? So all right, I've got this translation, or excuse me, this transformation T of Z, and I want it to just rotate by theta. So we're gonna pick two lines. The first line is just the real axis. So the first line is just this one, the horizontal axis. That's gonna be L1. The second line is going to be a line through the origin that has angle theta over 2 here. And amazingly, this works. These are the two lines. So let's convince ourselves that this works. And I've had my jollies convincing myself of this a couple of times, so hopefully I can do it in front of y'all. So let's say here's my point Z, and I want to rotate that by theta. So let's just notice what Z is in polar form, specifically its angle. So let's just say that angle is alpha right there. And actually it's kind of like negative alpha, right? Well, it's a negative angle. So I went down alpha radians or degrees to get to Z. Okay, our first step is flip over L1. That's just conjugate, right? So flipping over the horizontal axis is just taking the conjugate. So step 1 is flip Z over L1, i.e. take Z conjugate. So I'm going to flip that up. And then this little angle here is going to be alpha, because that angle's just mirrored there. So this is reflection over L1 of Z. Stop for a second. Tell me if that looks cool. I got one more flip to do, and now it's going to be flip over L2. So now I'm going to flip this over L2. And let's see what we got here. So this is going to be the next flip to here. So, okay. So I want to make sure I'm not making any assumptions here. Now I'm starting to not be sure, but I know this works. So now we have to piece it together and be kind to each other. Oh, yeah. Okay, so let's see what we got here. So this is alpha, and this was theta over 2. So this thing right here, hold on, let's see. So I'm flipping that over. I gotta convince myself of this again. So I put that over there. Well, let's see. So if this is going to be, this little sub angle in here is going to be theta over 2 minus alpha. Just the one from that made this subtracted from that. So that means this angle over here in its reflected image is going to be theta over 2 minus alpha. Right? Because that angle is going to be the same. If I'm flipping over that, this little angle here is going to be the same as that one up there. So what is the net angle that I now have on, well, shit, it worked, I believe. So check it out. What is the total change in angle here? Well, it's going to be that angle plus that angle. But wait, I've got the minus 2 alpha in there, right? Why is that? this thing has angle alpha. This had angle, what is the angle we're shooting for? So let's take a look at that. So this has angle minus alpha. So what I want to show is that the reflected image has angle minus alpha plus theta.
Well, if
Yeah.
L2 splits the 90 degrees in half, wouldn't that make the other half alpha, and then you're subtracting?
If it were a perfect diagonal, that would be absolutely true. I was picturing, and I made that in my head, I think I was doing that too, that it's not a 45-degree angle, unfortunately. But if it was, that argument would be so solid. Luke?
So you've got the theta over 2 minus alpha, so when you add those up, you do get the theta minus 2 alpha, but you're not counting that alpha above the x-axis.
Right, I forgot
So
to
you
add that. Thank you. Yes, awesome. Okay, cool. So the net angle here is going to be theta over 2 minus alpha plus theta over 2 minus alpha plus that little theta there, or that alpha there. And then when you work this all through, we get theta over 2 minus alpha, which took the original angle and I got theta, and added theta to it. Solid. Okay. Thanks. Thanks, Morgan. Appreciate it. And now you may or may not believe me, but you could probably pull this back out. Yeah. That's kind of all I wanted to do today. So what your plan is for Monday is to actually start understanding inversion. That's your only thing. No homework. There's a homework now. I'm not going to give you a new one because, good Lord, I have stuff to grade and get you back anyway. We'll just have that quiz on Monday. If you have any troubles or questions, email me. We'll figure it out. Thanks, friends. It's like geometry. Hi. Yes, ma'am. Hi. Oh, okay. Cool. Okay. So now you have to find the square root. So that's the hard part. So now you need to find the square root of -2 minus 2I. So that means, so you should review, let's go back and check out these examples in your class. But the first thing to do is convert that into So step one is math. So is Grace looking at this too, or she's?
Yeah, she was, I just had asked her.
You should learn this.
He's talking about the polar, for the square root of the question, I was talking about this morning.
Well,
It's quite
is how we do this.
That's what I figured.
So,
Like, that's not the first one.
this is a special angle, right?
How are your prints coming out so far?
It's like 30 over 60. Let me figure out which one of those it is.
Yeah.
But then, this
I'm
is the
still-
angle that you want.
Oh, no,
So
the
find
angle
that
is-
theta,
This one?
and it'll be a
Nice.
nice
Since
one.
the angles moving
That's
to
nicely
the
divisible by
rotation's
2.
moving with it.
And then
I
convert
am
this
from
number
I was like,
into.
A little bit. See, that makes sense.
Yeah.
So step one is to take this, convert it,
What's the L1 and L2?
and then your answer is going to be plus or minus the square root of this radius, which, and you can find out with the Pythagorean theorem.
oh yeah, I would love to draw other people, especially
I
if
think
you
it's
can
Yeah,
actually
okay.
just to,
relatively,
just to let
like
you know.
super creative
And
and
then
not
e to
realistic.
the I of theta over 2. And then you'll have to convert that back into rectangular form.
Yeah, oh my
So
gosh.
step, convert it to
That's
polar, take half the angle,
Hold on.
figure out where you land. Does that make sense?
I'll figure it out.
Does that not make sense?
I don't.
You're not sure that makes sense? Let's do one together.
If you'd like to do the same.
I'm just.
Bye. Yeah, I'll see you there.
Makes sense to me why the
Let's say I want to take the square root of I.
Attached to the K because you're moving it back when it's
So,
already been violated.
first I plot it out
I've
in
been
the polar
wrestling
form.
with it the entire class.
What is that in polar form? So
This,
there's
and
I,
then, like,
what is my,
I'm gonna stick with it.
That's valid. Yeah.
I'll see you later. Do you wanna study for the quiz on Monday during upstairs?
how many degrees?
What am I gonna see?
Yeah, cool. And do you remember what that is in
Yeah,
radians?
right.
No, you're fine.
Yes, man, I'm
Really?
solid.
Tomorrow's my only
And then
day.
the radius here is
Tomorrow,
one,
tomorrow
right? So it's
usually
just
is,
one.
but I'm going to bed.
So now I've got that.
Little school.
So the square root
It'll be fun. It'll be fun.
is
It'll
now
make
the
you
square
happy.
root of this thing.
Kim Meyer.
So think about how square
Never
roots
heard.
work.
I've
That's the
never
square root of one
So.
times the square root of this.
Cool. What grade?
Seven.
But then that's just the
Which is
power.
First time we have reason sixth grade doesn't count as secondary, but
Yeah.
that's lame.
What do you do
stupid.
with those exponents? You multiply, right? So this is e to the I pi over 4. And now I just come back to the plane, I plot that out, there's pi over 4, and I figure out what are my coordinates here. So convert that back into rectangular form. And I've got-
Okay.
And this one will turn into
Love you.
square root of 2 over 2 plus square root of 2 over 2i. And then I would do plus and minus that, because you'll have to do plus and minus in the quadratic form. That's the basic plan. Write some stuff up and shoot me a picture of it if you're worried about how things are headed, okay?
I have a quick question.
Yes,
Can I have my homework? I need to erase one letter.
sure.
I've been thinking about it since the beginning of class.
Oh, Lord.
So I was like,
Why don't you just find it?
yeah.
Good luck with the dinner tonight.
Oh, thanks.
Of course.
You wanna go? You can go.
Not particularly. I can't lie.
You do a good job.
You will. Good job.
I'll see you later.
Yeah, thanks.
There we go. Because I had to talk myself into this making sense.
Oh, and now it does?
Sort of.
Cool.
Because my thing is I wrote for the scale, like the dilation one, I wrote k z minus z naught plus k z naught.
Oh, yeah.
Because in my brain, it's like if you have a circle and z naught's over here, it should dilate that way. But then when you explained it, it was like it's gonna dilate that way no matter what. And so now it makes sense.
You're not coming to club, are you? 'Cause you got something to do.
I have to go to some meeting.
What is it?
I was gonna call it a silly meeting, but it's not a silly meeting.
It probably is. Oh, that's all on tape. Oops.